Part 3. Wave propagation in half-space of elastic medium. Because the Earth is half-space, then we have to study how the wave propagate in half-space. The wave in the shallow area of the free surface is called surface wave. Because the earthquake engineering is concerned with the impact of earthquakes in human beings and their environmental at or near the Earth's surface, and because the attenuation of surface waves along depths is slower than that of body waves, surface waves are extremely important. In seismic engineering, two kinds of surface waves are the most important. One is Realign waves, existing in homogeneous elastic half-space. The other is love waves, which requires a surface layer with shear wave velocity lower than that of the underlying half-space. There are other types of surface waves that are not particularly important from the point of view of seismic engineering. First part is Realign waves. Realign in 1995 first studied the wave near the surface of a homogeneous elastic half-space, which is now called Realign waves. To illustrate Realign waves, consider the plane wave shown in figure, assuming that the wave propagates along the x direction and the particle displacement in the y direction is 0, v equal to 0. If the positive direction of z is downward, then all particle motion occurs in the xz plane. Two potential functions, phi and psi, are introduced to describe the displacements in x and z direction. Equation A, U equal to d phi dx plus d psi dz. And another, v equal to d phi dz minus d psi dx. The volume strain or dilatation epsilon v is epsilon v equal to epsilon x plus epsilon z. Then submit this into the equation. X direction displacement and W Z direction displacement. Here, equation B is W. And then we do the derivative calculation of A equation and derivative calculation to equation B and calculate sum of it. Now we can simplify it that epsilon v equal to negative d phi square over dx square plus d phi square over dz square. Here is a negative Laplace calculation to phi, function phi. For rotation in xz plane, 2 omega y is du dz minus dw dx, We also submit that. Finally, simplify it, we get a Laplace calculation to psi function. The potential function is used to separate the expansion from the rotation. We saw that phi and psi are related to the expansion and the rotation respectively. Therefore, Realign waves can be considered as P wave and S wave at this time because the xz plane is vertical. The expression of the u and w are substituted into the equation of motion A and C. Let's see the equation A rho d dx d phi square over dt square plus rho d dz d over dz d psi square dt square, then equal to lambda plus 2g and times d over dx Laplace calculation to psi and plus g d over dz Laplace calculation to psi. And for equation B is replace x by z. The solution of the above two equations is pretend that psi t d phi square over dt square is equal to lambda plus 2g over rho times the Laplace calculation to phi, or is Vp square times the Laplace calculation to phi, and psi d psi square dt square equal to g over rho times the Laplace calculation to psi is Vp square times the Laplace calculation to psi. Now for Realign waves, we can find the motion caused by a typical plane waves propagating in x direction. This is x direction. And we can find the vibration amplitude will decrease with the depth. If the wave is a simple harmonic with frequency omega and the wave number kr, it will propagate with Realign waves velocity Vr equal to omega over kr. Then the potential function can be expressed as phi equal to Ez times the E powered by I omega t minus krx. Psi equal to Fz times the E powered by I omega t minus krx. Here, the functions E and F described the model of the amplitude variation of the Realign waves volume and the rotation components along the depths, respectively. By substituting the above expression into the wave equation 3.68, we get the result. We get this result. Equation A and B. And it can be further sorted into the second order differential equations as the 3.71. Let the general solution of the equation be Ez equal to A1 times the e powered negative qz plus B1 times the e powered qz. Fz equal to A2 times the e powered negative sz plus B2 times the e powered sz, where q square equal to kr square minus omega square over vp square, and s square equal to kr square minus omega square over vs square. And the second term in equation 3.72 corresponds to a disturbance whose displacement amplitude tends to infinity as the depth increases. Obviously, the behavior is impossible, so B1 and B2 are 0, and the potential function can be expressed as phi equal to A1e times the q powered e powered negative qz plus I times the omega t minus krx. Psi equal to A2 times the e powered by negative sz plus I times the omega t minus krx. Because there is neither normal stress nor shear stress on the free surface of the half space, that is, when z equal to 0, sigma z equal to 0, tau xz equal to 0. Then sigma z equal to lambda epsilon v plus 2g times the epsilon z, and equal to lambda times epsilon v minus 2g dw dz equal to 0. And tau xz equal to g times the tau xz equal to negative g times the dw dx plus du dz equal to 0. By using the definition of the potential function of u and w and the solution of potential function, the boundary condition at a free surface can be written as sigma z equal to sigma z at z equal to 0 equal to this equation 3.768, and tau xz when z equal to 0 equal to 0 the equation 3.76b is obtained by the simplification, right? Equation 3.77a and b. The velocity and the displacement of Realign waves can be determined using this equation. Now let's see the velocity of Realign waves. The equation 3.77 is multiplied by each other to obtain the equation 3.78. Let's see. The definition of Q and S is introduced and use the factors G square and KR square to normalize. Then we get the equation 3.79. Here KRS is defined as the ratio of Realign waves velocity to shear wave velocity. Then KRS just equal to omega over Vs times Kr. Then Vr over Vp go on is equal to alpha times the KRS. Here alpha is equal to square root g over lambda plus 2g, or square root 1 minus 2 nu over 2 minus 2 mu. So equation 3.79 can be rewritten as equation 3.82. Here, this equation. After expansion and simplification, we can get equation 3.83. This is a cubic equation above KRI squared. For different Poisson ratios, the real root solution of KRS can be obtained. For different Poisson ratios, the ratio of Realign wave velocity to S wave and P wave velocity can be obtained. The result shown in this figure. In this figure, we can find that Realign wave's velocity is slightly lower than the S wave's velocity for all the Poisson ratio except 0.5. Here, Realign waves less than S waves, only at mu equal to 0.5. They are same. Let's see displacement amplitude of Realign wave. By substituting the solution of potential function and into the expansion of displacement function u and w, the necessary partial derivation can be obtained. U equal to a1 minus a2. W equal to negative a1 plus a2. Equation 3.84 A and B. It is obtained from the equation 3.77b. Then a2 equal to negative 2qikr over s squared plus kr squared times a1. Now we get the relationship between the a1 and a2. By substituting it into the equation 3.84, then we can get u and w in equation 3.86 A and B. Now let's see the Realign wave. The items of brackets indicated the variation of the amplitude of u and w with depth. The following figure shows the horizontal and vertical displacement amplitudes for different Poisson ratio. The natural phase difference between the horizontal displacement and the vertical displacement can be found in equation 3.86. Therefore, when the vertical displacement reaches to the maximum value, minimum value, the horizontal displacement will be 0. And the motion of particles near the surface of half space is a backward ellipse, while the water wave is a forward ellipse. Contrary to the particle motion observed on the surface of water wave, the general behavior of Realign waves is shown in the figure in the following. You see, this is the horizontal component. The amplitude is amplitude of Realign waves, and this is horizontal components, and this is vertical components. And we use different Poisson ratios to discuss it. Okay. Then the Realign waves behave in undisturbed media as this, but in the soil, the behavior like this. Now let's move to love waves. However, when the half space is covered with a layer of surface layer with low wave velocity, love wave will be generated. This is proposed by Love in 1927. Love waves is composed of SH wave and SS wave is reflected and superimposed in the surface layer. Consider that homogeneous half space so in figure 312 is covered with a homogeneous surface layer of thickness H. The love wave propagating along the x direction will only be represented by the particle displacement SS wave in the y direction, which is described by the following equation. Vxz equal to amplitude Vz times the E part I times the KLX minus omega t. Here, V is the motion of the particles in y direction, and Vz describes the change along the depths, and the KL is wave number of love wave. In the surface and half space, love wave must satisfy the wave equations of S wave. Here, this is the equations 3.86. Aki and Richard in 1980 proved that the variation law of amplitude with depth is given in this equation. Vz is given in this equation. If this point is between the 0 to h depth, or if z larger than s depth, we can calculate Vz using equation 3.27. Here, the coefficients A and B represents the amplitude of downward and upward broadcast wave respectively. V1 equal to square root KL square minus W square over G1 over rho 1. V2 equal to square root KL square minus W square over G2 over rho 2. Due to the half space problem, due to the infinite depths, B2 must be 0 at infinite depths. There's no energy source and no reflection to generate upper wave. In order to meet the requirement that all stresses at the surface of ground are 0, dV dz we can calculate dV dz. Z is Vz is a Z function, and simplify it, we can get negative A1 minus B1 times the V1 times the E powered negative Vz plus E powered V1z equal to 0. It's equation 3.89. In other words, if A1 equal to AB1, the amplitude can be expressed by the other two unknown amplitude. Vz equal to A1 times the E powered negative V1z plus E powered V1z. This is for the depth from 0 to h. If depth larger than that, Vz equal to A2 times the E powered negative V2z. Requirement of stress constitutive condition at z equal to h. That's the 2ig1v1 mu1 a1 sin I v iv1h equal to g2v2a2 e powered negative v2h. Equation 3.91. Requirement for displacement compatibility conditions is equation 3.92. 2 times a1 cosine I v1h equal to a2 e powered negative v2h. Using equations 3.90 and 3.91, A2 can be expressed by A1 as A2 equal to 2 cosine IV1H over E point negative V2H times the A1. Substituting the above solution into equation 3.85, we get the solution of V is a function of x, z, and t. There are two equations. One is for the soil in the depth from 0 to h. Another is z larger than h. Here, Vs1 and Vs2 represent the shear wave velocity and material 1 and 2 respectively, and the Vl is the law wave velocity. As shown in figure 3.13, equation 3.94 shows that the displacement amplitude of law wave changes sinusoidally in the surface layer and decays in logarithmic spiral with depth in the underlying half space. Therefore, law wave is often described as an additional SH wave in the surface layer. The law wave velocity of the law wave is obtained from the following equations. Equation 3.95, this equation. As shown in the figure below, the wave velocity of law wave changes from the S wave velocity in the half space at a low frequency to S wave velocity in the surface layer at a higher frequency. The correlation of frequency indicates that law wave is dispersive